Welcome back. In this section, we'll be talking about finding the values of trig functions for any angle. In the previous section, we talked about acute angles, 30 degrees, 45, and 60. We talked about angles inside of a right triangle. But now we'd like to open up our discussion to any angle, whether it's a positive one or a negative one, whether it's something that's less than 90 degrees or more than 90 degrees. We need to be able to find our values of our trig functions. So that means that instead of talking about angles inside of a right triangle, we're now going to think about our angles as drawn in standard position. And so that's what I have here in my diagram. I've got this angle theta that I've drawn in standard position, and I've selected any point, doesn't matter what point you want, but any point that happens to be on that terminal side. And then we're going to find the distance from that origin to that point, and that distance between those 2 points, we'll call that r. And if you're using your distance formula, you would find that the distance from 0, 0 to that point xy is square root of x squared plus y squared. So that's what r will be. That will be our distance. So one thing to note here is that even though we're going to be talking about angles that are in standard position, there still is a right triangle going on here. If you were to take our point xy and draw a line going down to the x-axis, you can see that we do indeed have a right triangle. And if you're thinking about this right triangle, for the angle theta, that angle is next to the x side. So the x side, in a sense, is kind of like our adjacent side. The side that's opposite to it would be the y side. And of course, that value of r that we have, that's our hypotenuse. That's the hypotenuse of that right triangle. Now, the one thing that's going to be different here is that when we were dealing with right triangle trig, we had that it was 3 sides of a right triangle, so all 3 sides had to be positive numbers. Now, the value of r, since that's a distance, that is going to be something that's positive. So for sure, r is always going to be not negative. However, the values of x and y, since they're coming from our point that's on that terminal side, then x and y could be positive or could be negative depending on where we are. For this angle that I've drawn, whatever the x-coordinate is, it would happen to be something negative. So that means that I would have a negative value for the adjacent side, and I would have the y value as positive. I would have a positive value for the opposite side. So that means that when we're looking at angles that are in standard position, we're going to wind up having things where our trig functions aren't always going to be positive in value, unlike when we were talking about our triangles, our right triangle trigonometry. Now, the way that we're going to define our trig functions, it is going to be in terms of x's and y's and r's. But if we remember what I had just said about really the y side being the opposite side and the x side being the adjacent side and r being the hypotenuse, you can see that essentially these are the same definitions. So, for example, we are defining sine of theta as being y over r, but remember that y was the opposite side on our little triangle and r was the hypotenuse. So in other words, it's the same definitions, just rewritten in terms of x's and y's and r's rather than opposites, hypotenuses, and adjacents. Now, one thing that's going to be true here that we didn't have to worry about in the past was that some of our trig functions will be undefined for certain angles. If you're remembering the way that we define things with all opposite, adjacent, and hypotenuse, those were side lengths in a triangle, so none of those lengths could be 0. However, if we're talking about x and y coordinates, it's possible that x or y, or both, could wind up being 0. So that means something like cosecant, which is the reciprocal of sine, that would turn out to be undefined anytime y is 0. So, for example, if we were talking about 180 degrees, then the x-coordinate would have some sort of negative value to it. So I could take, for example, the point -1, 0. And you could see then that cosecant would wind up being undefined for 180 degrees, since the y value would be 0. And so no matter what r is, you'd have something divided by 0, which is undefined. So that's something to note here, that 4 out of our 6 trig functions, tangent, cotangent, secant, and cosecant, all have the possibility of being undefined when either x is 0 or when y is 0, depending on which function we're talking about. Okay, so let's do an example here. We've got the terminal side of an angle is in standard position, and that side passes through the point 3, -6. So I guess the first thing that I'm going to do is I'm going to do a little sketch here of my angle. And so my point 3, -6, around there. So that means that my terminal side is right here. And so the angle that we're talking about going from the positive x-axis to that terminal side, that would be my angle theta. So this angle, whatever it is, it's something somewhere between 270 degrees and 360 degrees. So this angle, we now know that it is over there in that bottom right hand side. That's where that terminal side is. We know the value of x, that's 3. We know the value of y, that's -6. And so before we can find the values of all of our trig functions, we'll need to know the value of r. And this is where we'll use our formula that we have, that r is square root of x squared plus y squared. Don't forget, of course, when we're squaring x and y, we're squaring the negative as well. So in the case of x squared, that's 3 squared, which is 9. Y squared, -6 squared, that's positive 36. So r is root of 45, which in simplest terms, that would be root of 9 times root of 5, which is 3 root of 5. Okay, so now we've got almost everything we need. We needed our value for x, for y, and for r, and then once we do, we can find all of our 6 trig functions. So the definition for sine of theta, that was y over r, or -6 over 3 root of 5. And then we just need to simplify this, the 6 and the 3 canceling, and then rewriting this in simplest terms by rationalizing that denominator, -2 root 5 over 5. And once I know sine, I know cosecant, so let's give that. Cosecant of theta, that's the reciprocal of sine. Since sine was -2 over root of 5, then cosecant should be root of 5 over 2 negative. There we go. So we've got 2 out of our 4 trig functions. So sine and cosecant. Let's do now cosine. Cosine of theta, that's x over r, or 3 over 3 root 5, which, again, simplifying this and making sure that the denominator is rationalized, we have cosine of theta being positive root 5 over 5. And once we know what cosine of theta is, we can find its reciprocal, secant of theta. Cosine had a value of 1 over root 5, so secant should be the reciprocal of that, root 5 over 1, which is just root 5. And then finally, we have tangent and cotangent. Tangent of theta, that's y over x, which is -6 over 3, which is -2. And cotangent should be the reciprocal of tangent. If tangent was -2, then cotangent should be -1/2. So there's one thing that I want us to note here, and that's for this angle that we're talking about, 4 out of our 6 trig functions happen to have negative values. That for this particular angle, sine was negative, cosecant was negative, tangent was negative, and cotangent was negative. And one thing that we'll talk about a little bit later on in this section is how where the angle is will affect whether the values of our trig functions are positive or negative. So for this particular angle, ending there in this bottom right-hand side, those 4 trig functions, sine, cosecant, cotangent, and tangent, are negative, and for that angle, cosine and secant is positive. And we'll see different patterns emerging in the other 3 quadrants. Okay, so here we go. We've got one other little bit of business to tackle here, and this is one where we have an angle that's in quadrant 3, and we know the value of tangent of theta. So to begin with, we know that tangent of theta is defined as y divided by x. And here, tangent of theta is 4/7 positive. So that means that there's actually 2 possible options. Either both x and y are positive, so you could say that y is positive 4 and x is positive 7. That would give you a value for tangent of 4/7. But you could also say maybe y is negative and x is negative. Y being negative 4 and x being negative 7, that would also give you that value of 4/7. That's the reason why in the problem I'm telling us what quadrant our angle is in. And that's because depending on which quadrant we're in, tangent might be positive in more than one place. So here, tangent can be 4/7 actually in 2 different places. But for this question, our angle happens to be in quadrant 3, and we know that in quadrant 3, if we're remembering our quadrants, that in quadrant 3, the x-coordinates should be negative, and also the y-coordinates should be negative. So that's how I know that it's not positive 4 and positive 7 for x and y. That would be if we were in quadrant 1. So let's say this. We know that our angle is in quadrant 3, and we know that in quadrant 3, that the x value must be negative, and also the y value must be negative. So that means that if tangent of theta is 4/7, then that means that the y value must be negative 4, and the x value could be then negative 7. I'm actually being a little bit loose here when I say that the y value must be negative 4 and the x value must be negative 7. That's not strictly true. It is true, though, however, that for that angle, that negative 4 for y and negative 7 for x, that would be a point on that terminal side. But of course, you know that our angle that we're looking at, we could have taken any other point that happens to be on that line. And you could see that, for example, you could have just as easily taken a y value of negative 8 and an x value of negative 14, and you would get exactly the same 4/7 for tangent of theta. So not strictly true when I say that negative 4 and negative 7 must be the values for x and y. You could have chosen other ones as long as y divided by x is 4/7. But it makes easiest sense here that if tangent of theta is 4/7, to just say that y must be either positive or negative 4, and x must be either positive or negative 7, depending on what quadrant you're in. And that's how I've come up with my point here, that x is negative 7 and y is negative 4, that would be a point on that terminal side. And away we go. We can now find our value for r by saying that that is square root of x squared plus y squared. And just using what we have here for x and for y, x is negative 7, and when we square that, we'll get 49. And y is negative 4. When we square that, we'll get 16. And so r should be root of 65. And that root is in simplest terms. There's nothing, no perfect squares that can be taken out of it. So we are good to go. We'd like to find both secant of theta and sine of theta. So let's do sine of theta first. That's just y over r. And the y value was -4. And r was root of 65. So we get -4 root 65 over 65 when we write this in simplest terms. Next part, finding secant of theta. I'm just going to use the fact that secant and cosine are reciprocals. So first I'll find what cosine of theta is. Cosine of theta, I know that that's x over r. And that should be -7 over root 65. I'm not writing this in simplest terms because this is actually not the end of my work with this. I'm going to now say that secant of theta is the reciprocal of cosine, and that should be then negative of root 65 over 7. That was the reason I didn't bother to rationalize the denominator here, because if I rationalized the denominator, I would just have to undo the work that I did when I took the reciprocal. So I looked at what I had, -7 over root 65 for cosine, and I realized that I could take the reciprocal of that to get secant, and that what I would have would be in simplest terms. So there we go. We have now our value for sine of theta and also for secant of theta.